Okay.
Yeah. All right. Well, thanks a lot for doing this, and take it away, Pengchen.
Okay. Thanks, David. Hello, everyone. Thanks for being here. Today I will talk about some of my postdoctoral work, and the title is Evaluation of Global Total Water Level Model in the Presence of Radiational S2 Tide. And I would like to acknowledge my supervisor, Natasha, and my co-authors, Keith. Keith is here, and Subasa in the University of Turku. First, this slide show you an overview of the global system. It's a global deterministic surge prediction system, and it's based on NEMO. It has a 1/12 degree resolution, barotropic. It has tidal nudging to support tide prediction. And this will be a new system to be installed in spring next year, and the replacement of to the regional system. Motivation. The motivation is that there is a need for total water level forecast for the benefits of Canadians because Canada is surrounded by 3 oceans. And for this purpose, we choose a global model because firstly, it allows enough room to include the coastal waveguide and thus avoid the trouble dealing with multiple boundaries. Secondly, it allows the inclusion of sea level contribution from any global processes. And one example is the global response to the atmospheric S2 forcing. And this will be one of the focuses in this study. So specifically, we are going to address the 2 following questions. Firstly, we look at how to make tide as good and possible due to the given the limited resolution in a global model. And here we introduce the tidal nudging approach. Next, we look at how best to construct a total water level model. That is, we look at is it more beneficial to run the tide and the surge model separately, or should we run the combined tide surge forecast? The observations we used in this study include the TPX-08 global tidal solutions, and which is constrained by the satellite altimetry data. And here we treat it as observations, and we use the eight major tidal constituents. We also have tidal gauge data from a global array of 304 gauges obtained from the Sea Level Center, University of Hawaii during the year 2008. And in order to better clearly show the results, we reordered the gauges going around the continents, and we separated them in 8 subregions. And so in this way, we can draw the results by sedition code and better show the model results. The model is barotropic based on the depth integrated momentum and continuity equations. And yes, the changes we made on the equations is that we include the self-attraction, the loading term, and the internal wave drag term to support tide prediction. And in this study, we add the tidal nudging term on the right side of the momentum equation. And here, the gamma is the nudging coefficient. You can see it controls the strength of the nudging, and you can see it can be spatially varying. And the angle brackets denote the tidal filter. And you observe comes from the TPX-08 data. In addition to nudging U in the momentum equation, another approach is to used by a previous study is to directly nudge it in the continuity equation. But apparently this approach has a potential issue because it changes the mass conservation. And in this study, we'll show a comparison between these 2 approaches. The model is based on NEMO, and here we choose 12-degree resolution because we did a sensitivity test with a lower and higher resolution, and we found that A quarter degree is insufficient to adequately forecast the surges, while 1/36 degree leads to only localized improvements, but at a considerable increase in cost. And below are the changes we made on NEMO. And the changes we made in this study is that we extended the model grid to include in the Southern Ocean to include the Ross Sea and the Weddell Sea, and to allow this allows the tidal propagation under the ice shelves. And we found that this is important. This is very important for accurate tide predictions in the Southern Ocean, even to the lower latitudes. Another important changes is that we implemented the tidal nudging approach. For the nudging, we only nudge the deep water because we want to allow surge and nonlinear processes to freely evolve on shelves. So we set the nudging coefficient to be 0 on the shelf, and in deep water it's depth dependent. The atmospheric crossing is based on the global deterministic reforecast system developed and ECCC. It has about 39 kilometer resolution and is hourly. And we found that there is a S2 component in the forcing. And here shows the S2 winds and the pressure. And this is important because it can trigger a global ocean response known as the radiational S2 tide. And to study this issue, we separate the forcing into a non-S2 and a S2 component. And we will come back to this issue later. In order to investigate a number of different issues, we set up the following experiments. And firstly, we have 3 tide-only run. One is without nudging. The other 2 is either nudging U and nudging eta. So by comparison, we can see the effectiveness with the nudging and the comparison with the 2 different approaches. Next, we have 2 surge-only run, with and without the S2 forcing. And by comparison, we can see the impacts with the S2 forcing. Next, we have 2 combined tide surge forecast runs, with and without nudging, to look at how best to construct the total water level. First, I will introduce the tidal nudging approach. This approach is novel in the sense that the nudging is only applied in specific tidal frequency bands, and outside these bands, the model dynamics are not directly affected. It has 2 important parameters. One is gamma, as we introduced earlier. Another one is kappa. Kappa controls the width of the frequency bands to be nudged, and the spin-up time with the filter. For example, a smaller value of kappa corresponding to a large spin-up time, as well as a small width of frequency bands. So to illustrate this approach, we applied the tidal filter to a total water level record, composed over tides and surges, and the surges simulated by AR1 model. And the total water level record is shown in panel A. And in panel B, we show the original tides and the filtered total water level by the tidal filter. And in this case, we use a spin-up time corresponding to about 14 days. And we can see that after about 2 T-spin time, that's about 30 days, the tides are very well recovered by the filter. And meanwhile, the surges, which is shown in panel C, come through almost unchanged. And this is important because this indicates that the filter will not suppress the surges in the deep water in the global application. And next, we further look at the sensitivity, show the sensitivity of the filter to two different kappa values corresponding to a spin-up time of 14 days and 5 days. And here in panel D, it shows the errors in tide. And the red lines for the 14 days, the blue lines for the 5 days. You can see when we decrease the spin up time, the errors in tide increases. This is because that the width for the frequency bands is also increases, and this leads to the contamination with surge energy in the tidal frequency bands. And in the global application, we found from sensitivity test, we found a kappa value that corresponding to 14 days is sufficient to acquire relatively accurate predictions without significantly increasing the spin up time. Next, we look at the comparison with the two different nudging approaches, nudging U and nudging eta. And we compare with TPX-08 data to which the model is nudged. And on the top panel shows the errors in M2 tides for the 3 tide-only rounds. On the left is for the tide-only round without nudging. The middle one is for nudging eta. On the right is nudging U in the momentum equation. And we see that both approaches lead to significant improvements for tides in deep water. But as we mentioned earlier, nudging eta will change the mass conservation, and a fair comparison is to compare the simulated tidal currents, which is shown in the bottom panel. And here we see that the nudging U shows the smallest errors. And this also indicates that by simply nudging eta will not help correct U through the momentum equation over some regions. And next, we show a comparison with the tidal gauge data, where the nudging is not applied. And here we draw the results by solution code. And here the black line shows the RMS with the observed tides, and the blue lines shows RMSE produced by the tide-only run with nudging eta, and the red line is for nudging U. And clearly we see that nudging U shows slightly better performance with at some stations in the Americas and Australia. So overall, we demonstrate that nudging U is the best approach to be used. Next, we look at the ocean response to the S2 atmospheric forcing. And here in the top panel, we show the S2 air pressure and the ocean response. And we see here, although the forcing is confined to the tropics due to the thermal radiation, but the ocean response is global. Actually, this process is similar to that for the gravitational tides. And similar to the gravitational tides, the largest two values or RS2 tide are found in the Bristol Channel and the Belfundy, and it can reach 88 centimeters. And next, we look at the impacts with the temporal resolution. When we decrease the resolution from hourly to 3 and 6 hourly, we see both the forcing and the responses are greatly reduced. And in particular, from hourly to 3 hourly, the result seems to be simply reduced by a scale factor. And actually, this can be mathematically verified. For example, if we consider a simple sine wave and we subsample every 3 hours, and we do the linear interpolation and 1 hour interval, and we found that the strength of the subsampled signal is about 22% of the original signal. But from 3 hours to 6 hours, it's not that simple, and it depends on the phase where you pick up. For example, if you pick up the nose, then you will get nothing. And lastly, I want to mention that in this case, we exclude the nonlinear interactions associated with the RS2 tide, which will be discussed in the next section. Now, in this section, we are going to use the tidal gauge data to evaluate the model scale in predicting the tides, surges, and total water level. And here the top panel shows the RMSE map in the tidal only run with nudging, and the middle panel shows the differences in RMSE between the two tidal only runs without and with nudging. So basically, the warm color indicates improvements by the nudging. And in the bottom panel, we also draw the results by the station code. And overall, we found that tidal nudging improves the model scale at 82% of the 304 stations and reduces the average RMSE by 23%. And we also note that the tides in round 10 are nudged to TPX08. It thus contains both gravitational and radiational components, and this is consistent with the tidal gauge data. And finally, we found that the model performance is comparable to the data asymmetry model FES 2012 used by Moise in terms of the average RMSE. Next, for surges. For surges, we need to evaluate the model scale in surges, we need to remove the radiational S2 tides in run S to be consistent with tidal gauge residuals, because in the tidal gauge residuals, the S2 is also removed by T-tide. And for this purpose, we remove RS2 by removing the S2 component from the forcing, which is run S prime. And the RMSE in this run is shown in the bottom panel, top panel. In order to show the effects of the S2 forcing, and we further show the RMSE differences between the surge only run with and without the S2 forcing, and again the warm color indicates improvements by removing the S2 forcing, and here we see that by moving the S2 component leads to better fit with the tidal gauge residuals at and stations that with a large RS2, such as the North Sea and the northwest of Australia. And in this evaluation, we also we want to note that we filtered out the low frequency signals because we want to focus on the high frequency signals generated by the atmospheric forcing. And I also want to note that the model has some limitations over the tropics, such as the Pacific and Atlantic islands in the ocean, due to the limited resolution in both the model and the forcing. This slide further shows you the time series for observed and predicted surges in the 2 rounds and 3 selected stations. And here the black lines for the observed surges, the blue lines for the surge only run without removing the S2 forcing, and in the red line, the S2 forcing is removed. And clearly we see a S2 component in the blue line, and you can reach 40 centimeters and Cook's Haven. And by removing this, removing the S2 forcing lead to much better fit with tidal gauge residuals. And another interesting feature is that there are still in the red line at Cook's Haven and Brest, there's still some remaining energy at near the S2 frequency, and this indicates that the S2 forcing over the tropics is not at a single frequency, and there are some energy that's close to the S2 frequency that cannot be removed by the tidal analysis. Next, we look at the nonlinear interaction associated with radiational S2 tide, and to our knowledge, this has not been looked at before, and the previous studies only shows the RS2 amplitude derived between the combined tidal surge run and the tidal only run, and which I show in the top red panel. On the top left panel, it shows the RS2 derived from the surge only run. So if we subtract these two panels, we can see the effects with the nonlinear interaction. And this is shown in the bottom left panel. Here we see the nonlinear interaction greatly reduced the RS2 amplitudes over regions with larger S2, such as the Patagonian Shelf and North Sea. To examine the causes, we look at the bottom stress and S2 frequency. And we derived the S2 bottom stress from case A, surge only run, and case B, the difference between these two runs. And in the bottom right panel, we show the ratio between in the S2 bottom stress between the runs with the inclusion of nonlinear interaction and the runs without nonlinear interaction. We can see that the nonlinear interaction greatly increases the S2 bottom stress over these regions, and this explains the damping of RS2 over these regions. Next, total water level. First, we analyzed the 4 possible scenarios to construct the total water level model based on the runs in this study. The first one is run T plus run S, and the drawbacks are that there is no tidal nudging, and there is no nonlinear interaction between gravitational and the RS2 tide. There is no nonlinear tide surge interaction. The second one is run TS, no tidal nudging. The third one, run Tn plus run S, and this is similar to the first one. There is no any nonlinear interactions. In addition, it also has a potential issue. It has an issue with double counting because both run Tn and run S contains the radiational S2 tide. The last one is run Tn-S, the combined tidal surge run with nudging, and it does not have any of the above mentioned issues. And it shows the smallest errors, which is indicated by the numbers on the right. It is the medium with the RMSE with the total water level predictions in comparison with the gauges. Next, we show this slide further shows you the RMSE map in the combined surge run with nudging. And overall, we found that the model scale is very good, and the average RMSE across all stations is about 0.50 meters. For comparison, it's 0.70 meters in another global tide and surge models used by MOIS. But we noticed that their number is evaluated based on 30 years results, and ours is based on 1 year's results. Next, we'll just show you the flow of the system and the resources. And with 1,440 CPUs, we can perform 10-day forecast in 20 minutes. In summary, we demonstrated that the tidal nudging is a very encouraging approach, and it improves tide predictions, and 82% with the 304 gauges, even though the nudging is applied only in deep water. Secondly, we found that we demonstrated that the combined tide surge with nudging must be used for global operational forecasting and climate sensitivity studies due to the interaction between the gravitational and we also show that the high temperature resolution forcing need to be used because both the S2 forcing and the responses are greatly reduced from the hourly to 3 and 6 hourly resolution. Lastly, in terms of the regional modeling system, we note that the RS2 will be mostly missed because with its origin over the tropics. Next step, we are going to we plan to to further improve the model by include the baroclinic effects, and we also find some we already found some interesting gains from the effects with the baroclinic effects on the coastal wave propagation, and also the seasonal variability. Okay, that's it. Thank you.
All right, thank you so much, Pengchen. That was very interesting. Do you have any questions out there in the audience? I see Jin has a question.
I do. I do have a question. A really good talk in Pengchen. So you use the NEMO, right? So it's a barotropical model. Is depth averaged or is it three-dimensional? So my real question is why, so for global tidal circulation model, use a NEMO, and you need to add, you want to simulate, right? You really just nudging is a kind of data simulation. You want to simulate the TPSO into your tidal circulation model. And really because due to some missing physics. So what are the major physics which missing your tidal model without nudging? That's my question, yeah.
Firstly, the model resolution is limited.
Yes.
So it limited the tide prediction, and.
But the NEMO is a barotropical, right? Three-dimensional barotropical, isn't it?
Yes, but we only use one layer.
So it's a depth average, isn't it? Depth average. Okay. Yeah. So the one of the issue related to the depth average, the tidal circulation model is the bottom fraction parameterization is quadratic function of the depth average of the tidal current. This is the one with kind of approximation you could have. Another one is the tide generating potential, right? You use it in your model, right? So so really I think there are several issues. One is related to the bottom fraction parameterization. Another one is how accurate your tide generating potential in your model, your model system.
Yes.
Okay, I see.
Thanks. Yeah.
But also another thing is that TPSO is that you could consider is a reanalysis of the tidal circulation in the global ocean, right? So, but also depends on resolution and the data simulation, right? TPSO. In your study, you consider is an observation, but TPSO is still is a data simulated model results, not kind of real observation.
Yeah, it minimizes the errors between the model and the observations.
Right, but again, the accuracy of the TPSO also depends on the resolution of the TPSO model and the number of the observation used in the TPSO. That's my real question. So over coastal water, maybe it's less accurate. I don't know. The TPSO I'm talking about.
Yeah, but we mainly nudge the deep water.
Deep ocean.
Yeah, we don't on the shelf. We don't nudge.
Okay, thank you, Pengchen.
Yeah. Thanks, Jimmy.
Yeah.
Looks like Dave Greenberg has a question.
Hi, can you hear me?
Yeah.
Okay, so a couple of hopefully quick, short questions. The gamma that you used for the nudging, it looked to be spatially variable. What kind of magnitude did you use for that?
I will show you the slide. Gamma. Oh, it's here. Yeah. Yeah, we set a maximum is 0.05.
Okay. Oh, that's it. Okay.
Yeah.
Yeah. Very good. Okay. And it's just in the deep water. The deep water starts where, or is it? What was the edge of the deep water? 1,000 meters, or?
Yeah. Sorry, I kind of forgot. Probably. Yeah, I need to check it. Sorry,
Okay.
David. Yeah.
Yep. Okay. The FES crew, they've done atmospheric tidal models, Lauren Carrere, and have you done any, like at Geophysical Research Letters 2003, have you done any comparison with their work?
For the atmospheric tide?
Well, they've done the full tide surge global model with the FES series, and then they've got at least a short publication on that in Geophysical Research Letters, and I believe that's what they're using for their satellite correction. And I'm wondering if there's any comparisons you've done with their work. It sounds like they're producing similar sort of products.
And sorry, David, can you see that paper again? It's in 2013?
2003, Carrere, C-A-R-R-E-R-E,
Oh.
and Liard, L-Y-A-R-D, and
Oh,
it's
yeah.
Geophysical Research Letters.
Yeah, I think I saw that paper. It's mainly for the surges, right?
Well, they've added the surges, but I think they've combined it with the tides. So I think it's a combined model effort. It's a tide surge. I didn't think it was just atmosphere. I thought it was just atmospheric forcing. I thought it was atmospheric forcing and the full tides. I thought it was a similar effort to what you were doing.
Yeah, I think 2003 paper they use like 6 hourly forcing, and
Oh, okay.
yeah, this cannot result.
Yeah. Okay. And then one minor comment. S1 is also forced by the radiation time. Tends not to be. It tends to be pretty small in some places, with the exception, I believe, of the Indian Ocean. Did you do any examination, any looking for S1 or in consideration how that might be affecting things?
Okay, thanks. Yeah, because I think yeah, S1 is small, and I didn't look at it.
Yeah. Okay.
Okay, sir. Thanks, David.
All right, thanks a lot, Dave. If there's anyone else out there, it's your chance to get in. Keith.
Yeah, Dave, can you hear me? Okay.
Yeah.
Yeah, okay.
Oh, hi, Pengchen. Nice talk. I have a question about the very last conclusion on the last slide. Just to make life difficult for you. Comes back to this question. You know, how come surge models, regional surge models, have done so well in the past, right? And so if you look at that last conclusion, RS2 will be missed in most regional modeling systems. Is that true if you were to radiate about TPXO at the open boundary? Because you would include RS2.
Yes, Keith. If the boundaries has information, you could include RS2.
Yeah, but that would So if you use TPXO for the boundary, the open boundary of the regional system, you may be okay. So
you may
want to phrase that a little bit more carefully. Yeah. Thanks.
Yeah, thanks, Keith. Yeah.
Okay, thank you, Keith. Is there anyone else out there? Last question? No? Okay, well, thank you very much, Pengchen. It's very interesting and nice to see you again.
Thanks, David. Yeah.
All right, thanks everyone else for coming.
Thanks.